Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. A couple of weeks ago, I had the pleasure of attending the NeurIPS conference in Montreal. I had a wonderful time there, and of course, the highlight was the chance to meet a ton of TWiML listeners. I held two fun meetups at the conference. The first was focused on AI in production and AI platforms and infrastructure, and it attracted a pretty nice crowd. We basically took over a dumpling restaurant in Chinatown right by the convention center. I also held a listener meetup one evening and got to hang out with listeners from all over the country and world. Of course, I took advantage of the opportunity to sit down with a few of the many great researchers attending and presenting the conference. And this week on the show, we're excited to share our 2018 NeurIPS series. In this, the first episode of the series, we're joined by Kunle Olukotun, professor in the Department of Electrical and Computer Science at Stanford University and chief technologist at Sambanova Systems. Kunle was an invited speaker at the conference this year, presenting on designing computer systems for Software 2.0. In our conversation, we discussed various aspects of designing hardware systems for machine and deep learning, touching on multicore processor design, domain-specific languages, and graph-based hardware. We cover the limitations of the current crop of machine learning hardware, such as GPUs, and peer a bit into the future as well. This was a fun one that I know you'll enjoy. And now, on to the show. All right, everyone, I am here with Kunle Olukotun. Kunle is a professor of electrical engineering and computer science at Stanford University, as well as the chief technologist at Sambanova Systems. Kunle, welcome to This Week in Machine Learning and AI.
Thank you.
So you just came from giving a talk on designing computer systems for Software 2.0 here at NeurIPS in Montreal. And I am really excited about digging into the topic of your talk. But before we do that, I'd love to learn a little bit more about your background. How did you get started in kind of this intersection of computer systems, architecture, and machine learning?
Yeah, so I've been in computer architecture for a long time. I've been at Stanford for almost 27 years. And I had done a lot of work in computer hardware. In fact, many of the ideas that underlie multi-core microprocessors were developed in my lab in the mid-90s before they became mainstream. And I did a company, a startup. It was called Afara Web Systems, and we did some high throughput processors for the data center, and it got acquired by Sun Microsystems, and subsequently Sun was acquired by Oracle, and all the big Spark servers were basically based on the technology that was acquired back in 2002. So I have a long history of kind of doing hardware. About 10 years ago, I sort of transitioned, after I came back from doing the first startup, I realized that the issue going forward wasn't so much, building new hardware. It was actually getting programs to run efficiently on that hardware, and getting programs at all, right? And so
we bought into the write once, run anywhere at Sun, right?
Right.
Big part of the mission there.
Yeah. Well, of course, the joke was write once, debug everywhere. Right. I think Java didn't help the cause really. It made things worse from an efficiency point of view, right? So, certainly you could imagine that maybe it made developers more productive, but that's arguable too.
Yeah. We're still garbage collecting to this day, right?
Yeah, exactly. So anyway, about 12 years ago now, we started thinking about, how could we kind of make a difference to the application developer? How could we make their life easier? And, you go back to sort of 2006, 2007, and it was clear that the world of of high performance hardware, which is a world that I have spent most of my life in, wasn't just parallel cores, right? It wasn't just multiple CPUs. It was also these new up and coming things called GPUs, and then of course it wasn't just shared memory. It was also clusters, right? And people wanted to program these things, and yet every program you needed to write needed to be different for the particular platform that you wanted to run on, right? And that, to me, seemed like a real problem from the point of view of the software developers. And so what we decided the right approach was to look at using domain-specific languages, right? Mm. So domain-specific languages had been around, and you probably are familiar with them, but let me just define them just for the sake of to make sure that everybody understands what they are. So the domain-specific languages, as the name suggests, are designed for a particular domain, right? That was a particular problem domain that you want to solve. And so if you can give the programmer both the operators and the data types that match that domain, then you make their life a lot easier, right? A really good example, since we're talking about machine learning, would be MATLAB, right? So matrix and linear algebra, you give yourself a bunch of matrix and linear algebra operators and data types, matrices and vectors and so on, and then now you can write your algorithms with linear algebra much more easily. So,
So it sounds like, if I can interrupt, it sounds like you consider MATLAB to be a DSL.
Yeah.
Which suggests to me that there's a spectrum of domain specificity.
Yes.
In the DSL world.
Right. Yes, there are absolutely. So, I mean, there are other examples that are, different domains. SQL's another example, right? Different domain, but again, MATLAB may be a bad example since you could probably use it to program almost anything. But the question is, how efficient would it, if you wanted to write an operating system using MATLAB, right. Probably not be a good thing to do. So there's this notion that, it really should fit the problem that you're trying to solve. Uh-huh. But, the thing about MATLAB that is a good example of the kind of initial approach of domain-specific languages is that they weren't really focused on performance, right? Mm-hmm. They're focused on productivity and not performance, mm-hmm. right? And it was almost the sense that, hey, you had to give up one to get the other. Mm-hmm. And so the research approach that we took was to say, look, there's some real value by using the abstractions provided by the domain-specific languages. They're higher level. They're more declarative. You're saying what you want rather than, how to get it, right? So the example would be, MATLAB says, hey, this is matrix multiply. If you do that in C, you write a bunch of loops, right? I don't know what to do with a bunch of loops, right? But I do know what to do if you tell me it's matrix multiply. Mm-hmm. So that raising of the abstraction level was something that could be a driver for high performance if you had the right sort of compiler technology. So I don't want to rat hole on the compiler technology that we developed, but it was really cool and it did all sorts of things, including enable you to take a high-level MATLAB-like program and run it without modification on the whole range of computing devices you might see in the data center. So multicore, GPU, cluster, or any combination mm-hmm. of the like.
The running on them isn't usually the problem. The problem is taking advantage of them. Presumably, it's taking full advantage.
It's taking full advantage. No. Yeah, running. Yeah, right. You could have one CUDA thread, and it wouldn't do much good. No. Yeah,
I'm just thinking of all the apps that are running on my laptop, and I just see one of the cores lit up.
No. By running, yes, actually getting good performance. Yeah, and hopefully close to what you would have gotten if you'd had written in this low level thing, right? Mm-hmm. So. If the low-level programming languages were CUDA for a GPU, could you take this high-level representation and get to the performance level that you would have gotten had you written the CUDA? Mm-hmm. Right. So that's what we're talking about, right?
Yeah.
But thank you for clarifying that. And then, but what that got us into was this whole realm of data analytics. Uh-huh. And so we started looking at how to do SQL and Spark and machine learning. And we, in fact, defined a new DSL for the machine learning world that we called Optimal. It was just a play on, but it was spelled OPTIML, right?
Of course.
Of course. And it was 2008 when we kind of defined it. So ML hadn't really taken off then, but it was, so we like to think we were ahead of the curve.
Absolutely. Sounds like it.
Yeah. So that was kind of the impetus for kind of our playing in this whole machine learning space, right?
Okay.
There's a notion that, hey, this we can define DSLs, we can do machine learning algorithms, we can write them easily, we could run them efficiently on a whole range of architectures. I should note that the other piece of technology that we kind of relied on was all these DSLs were not what are called standalone DSLs. So an example of a standalone DSL would be the examples I gave before, MATLAB, SQL, they're standalone, right? An example of an embedded DSL would be something like TensorFlow, right? And so all our DSLs were embedded in Scala.
Okay.
And, one thing that I mentioned in the talk, I'm an academic, so it's all about sort of putting your stake in the ground from the point of view of an idea and then seeing, who came after, right? And did they cite you? So we did Optimal, as I said, in 2008, and TensorFlow's later. But TensorFlow, if you look at all of these data analytic applications, machine learning, you'll see that, of course, essentially you can describe them at some level of abstraction as a set of operators with data flow arcs between them, right?
Right.
They all look like that way. And you define the operators may look different, but they fundamentally all look that way. And so, what we wanted at the end of the day was a data flow graph. Mm-hmm. And the question is how you get it and how you describe it. TensorFlow takes a very explicit way of describing your flow graph, right? But that's not the most natural thing to do. The most natural thing is just describe your program and then have the underlying infrastructure extract that graph. And so that's what we did, right? And so one of the slides in the talk, I showed, I say, here's K means clustering, right? Here's the 4 lines of code it takes in my DSL. And here's TensorFlow. It takes 20 because...
So what are the 4 in Optimal? What are the kinds of... I'm trying to get at the level of
level. So you have group by, right?
Okay.
Group the samples by their distance to the means.
Okay.
Great. You're done. All of a sudden, you've got clusters.
Nice.
Yeah. And now, then the other line is okay. Now go find the centroid of the clusters, and then you've got your new means.
Yeah.
So that I could describe it now, and anybody who kind of knows the group by operator like you do can grok it instantly, right? Yeah. As opposed to constructing some graph.
Right.
So that's the difference in the direction.
Yeah, and I think that's the idea that I was getting at with these, like the variations of domain specificity. Like you're operating at a way higher level of abstraction.
Yeah.
And so this DSL, you said 2008.
Yeah.
Has this continued to be kind of central to some of the things you've been working on since, or?
Yeah, so I think it was an early. So let me kind of just trace the arc of what we did, and then it'll become clear where it sits. So that was kind of okay. We had these DSLs embedded in Scala, but our thesis was, if you wanted to develop a new application, one DSL wasn't going to do the job for the reason that you just described. Is they were specific to So you say, okay, now I want a SQL piece. That means I need a SQL DSL. Mm-hmm. I want a machine learning piece. That means I need a machine learning DSL. I want a graph and analytics piece. That means I need a graph DSL. And maybe I can come up with something else, right? That you might need. And then you say, well, I've got this application that is going to use all of them in some way. We can argue whether they're going to use them sequentially and the data is going to pass between one, or whether the things are going to be more intertwined. But let's suppose that you have multiple DSLs. what you'd like to do is to be able to take a single application composed of multiple DSLs and do global optimization.
Right.
Right?
That was, yeah.
Yeah, okay. So that's what you want to do. And so in order to do that, right, I mean, the solution that comes to mind is to say, okay, why don't we capture the, since we said they all look like graphs anyway, right?
Right.
Could we figure out some underlying representation that's graph data flow like that all of these DSLs could map into, right?
So then you have dependencies and you can parallelize.
And then you can fuse across the boundaries of the DSLs and get rid of intermediate data and data movement, which is the scourge of any high performance implementation, right? And so that was the goal, right? Is to say, can we create, that was one of the goals. The other goal was this notion that, hey, you come up with a new domain area, but actually developing a high performance DSL is a difficult problem. So what if we could kind of remove the burden of the high performance part from you by creating a framework that allows you to develop new DSLs and then leverage all of this high performance compiler optimization infrastructure on top of that. So that was the goal. And so our view was, so we developed this infrastructure, we developed the framework. The DSL optimal was kind of the poster child DSL, the one that we put the most work into. And at the end of the day, we figured the real value was in the optimization framework, not in the DSL itself, right? And so going forward, we said, Scala has its issue. I think it has peaked and gone down in terms of popularity. It has all sorts of issues associated with the complexity of the language and the number of developers who kind of are conversant with it. And so, our view was it was too difficult to push a Scala-based DSL, but we could imagine pushing a Scala-based compilation infrastructure if the DSLs that you created came from somewhere else, right? So you can imagine, to kind of fast forward to today and you want to optimize TensorFlow, right? So TensorFlow will give you a graph. You take that graph, you give it to our framework, and then we can optimize it. Yeah.
And is that a theoretical idea, or is that actually what you're doing?
That's actually what we're doing. Yeah.
Okay. Which is a whole huge part of the system that you don't have to worry about anymore. You just need to take these graphs and figure out how to optimize them. Right.
So again, it's all about, actually getting application developers to use any particular language has its own set of issues associated with it, right? And Google's a much bigger entity than we could ever be in pushing that sort of thing. So why not ride on top of that and provide the added advantage that, hey, not only can you take TensorFlow, but you could take PyTorch and you can take SQL and you can take whatever, and you can change it to this representation. I should just say a little bit about the representation just because...
before you do that, a quick question. So the part of the vision here that was, these very targeted domain-specific languages, TensorFlow doesn't really get you there. Like there are some things in some areas that might be built on top of TensorFlow that would kind of get you there. Or do you think it does?
So I would view TensorFlow as a domain-specific language, right? Where the domain, again, is... matrix and linear algebra to a large extent.
Right. But so it's one of the DSLs that you might want to have a full system. Have you kind of moved away from, the idea that folks will develop very specific DSLs for specific, problem domains? Or do you think that will happen on top of TensorFlow?
It might happen on top of TensorFlow. It might be other languages that get developed. You ask sort of what the arc of the research. We decided that issue, that question is sort of what kinds of DSLs people want to develop. That is a very kind of domain specific question, right? And a question wrapped up in what languages people want to use and what abstractions really make sense. and we wanted to not have to develop new languages ourselves and get traction on those languages. And so rather we thought, well, okay, if there are existing languages, how can we accelerate them?
Okay.
And how can we provide a platform that might cut across a bunch of existing languages?
Okay.
Yeah.
So then I'm guessing that this platform serves as both kind of a center point for your research group at Stanford, but also ties to what you're doing at Sambanova?
Yeah, so the idea is definitely Sambanova has their own platform, which is different from the things that we. But so certainly some of the core ideas.
Okay, so then we can maybe come back to more on what Sambanova is doing. So please continue the thread on this system. We started talking about the connection between the software and the hardware, and we kind of left off at an optimizer, which is a software piece.
So let me fast forward to more recently, and about ML, and let's talk about. So about 6 years ago, Chris Ray showed up at Stanford, and he is a database machine learning expert, and we got chatting. And we started working together. We had a bunch of joint students, and he is a math whiz, and he's knows all about sort of theory, which I don't do. I'm much more of a hands-on builder kind of guy. But we started working together, and we started thinking about what one could do with machine learning algorithms to optimize them for modern hardware. And he came from Wisconsin, and one of the things he did was an idea for training machine learning algorithms using stochastic gradient descent (SGD) that allows them to be parallelized much more efficiently. But the interesting thing about his innovation is an innovation that nobody who didn't know anything about the algorithm would make, because they would have looked at that and said, if I do this, the algorithm is going to be incorrect.
Not something we want.
Not something we want, right? So, let me just tell a little story. So I teach a course in parallel software at Stanford. And there's one rule that I tell the students about parallel programming in what's called shared memory, right? Is this something your listeners would understand?
Some of them.
Okay. All right.
Sure.
Right. All right. So programming with shared memory. First rule: if you touch shared data, you should put synchronization around it. You should put locks around it, right?
Because there's a whole set of concurrency issues.
But basically, locks mean it's like go into slow mode, right? Essentially that means that when you've got a lock, there's only one. What you'd like is as much parallelism as possible. Whenever you take a lock on a piece of data, only one processor can actually be touching the data at the time, right? So if multiple processors want to touch it, the others have to wait, right? And that means that you're slowing things down. And just a bit of size as we talk about locking, right? What you would like to do is not use too much locking, because if you do too much locking, you'll create too much overhead. But if you don't do enough locking, you'll create what are called data races, right? Where you touch the data without locking. Wow. So people say, so the general conventional wisdom is, hey, if you touch shared data, you should take locks. But if you actually parallelize SGD by using locking, you do so little work based, when you take a lock, that you'll find out that all your time will be spent locking. That's all you'll ever do all day long, and that will just basically mean your program won't run very fast in parallel. So Chris Ray and his student came up with a idea they called hog wild, right? With an exclamation mark. And the idea is pretty simple. It says, throw out the locks. okay? And you say, that can't be correct. What you mean? I'm just going to touch the data willy-nilly? I don't know who, So sequentially, right, you're going to touch the data one iteration after the next to your SGD. Everything looks very reasonable. Now you've got a bunch of parallel processes which are updating the model in any fashion whatsoever. Mm-hmm. They're getting stale data, mm-hmm. right? There is no sequential order to the updates that you could match. Well, maybe there is, but it certainly isn't the case that I read something in the previous iteration and I'm updating it that this iteration. Could be I read it n iterations before. Right. The data's already been updated, and now I'm gonna change the model based on this, right? So all kinds of mayhem.
In other words, an idea that goes against the fiber of any distributed computing parallel programming.
Exactly. You got it. It's anathema to anybody who knows about programming. And you're saying, what the hell? What is this? But it works. And why does it work? You can prove it works as long as you don't delay updates too much. And it's back to this noise argument that we were having before. Mm-hmm. But fundamentally, stochastic gradient descent is a stochastic algorithm, and it has a bunch of noise associated with things. Mm-hmm. The model solution bounces around. So
just a quick note: we were having that talk before we started recording, so you should walk us through that again, because it comes up not just here but also when we talk about quantization and other places.
Right, okay, all right. So this notion about these algorithms, stochastic gradient descent in particular, which is the workhorse of machine learning training, and the basic idea, as you all know, is or maybe some of you know, is you've got a big data set. You take one of the elements of the data set, you estimate the gradient, and you move in the opposite direction, and then you update the model based on that. Now, if you have lots of processes or lots of threads that are doing this, then then what you'd like to do is you'd like to lock each piece of the model as you update it, so you make sure that only one processor, the processors all see a consistent view of the model. So, as I said, fundamentally, this update sometimes you compute a gradient because you're only estimating the gradient. The gradient sends you in the wrong direction, right? So you don't actually get, if you weren't doing stochastic gradient descent, then you would always go down the hill until you got to the optimum, which would be the global optimum if your function was convex. But if you're doing stochastic gradient descent, you can sometimes go uphill and you bounce around. So there's fundamentally noise associated with stochastic gradient descent, and you can prove, if you are so inclined, about how much noise you will see in a convex optimization problem, not deep learning. Deep learning is non-convex. So the question then is, if you do anything to perturb the process of getting to the optimum, you will add noise. And the question is, how much noise do you add? And can you bound that noise to be below the inherent noise associated with stochastic gradient descent? Mm. If you can prove that the noise you add is less than the noise that is already there, then you'll say you're not affecting the solution. Mm-hmm. So that's the nature of the proof. Mm-hmm. It's all about, reasoning about noise. Okay, so with that proof, you can think about how much noise you add based on how stale the updates are, and then you can prove that things will converge to the right answer at roughly the same rate as it would be if you had the locks in.
Even if you go hog wild. Wow, interesting.
Yeah. So that's and everybody uses it these days, right? Mm-hmm. Google uses it, Microsoft uses it. Everybody goes hog wild because doing anything else will slow you down dramatically. Okay, where were we?
We were getting to hardware, I think.
Oh, getting to hardware. Okay, that's right. So again, we were talking about. So that was the nature of a bunch of work we did together with Chris Ray. This notion of sort of what can you do with stochastic gradient descent to improve its behavior on modern hardware. Okay, so modern hardware likes to be very parallel. It likes to not have to, ideally you like to not use too much memory. Modern hardware likes to do things on small data types, think 8-bit integers, rather than 64-bit floating point, right? So that is the key thing about modern hardware. The other thing that was interesting about the work with Chris Ray was related to the things that I talked about at designing my talk, designing computer systems for software 2.0, was this notion that there are two big trends in computing today. One is exemplified by the thousands of people at NeurIPS, right? Which is the interest in machine learning and the broad applicability of the approaches and the dramatic improvements in applications, especially kind of high-end applications that have to do with doing things that humans traditionally have been good at. And that, of course, is causing everybody to get excited. And, one of the things that is true of building complex machine learning models is that they take lots of computation. Right. And if you look at why machine learning has been successful, it's because the computation has been available, right, to actually train these large networks, right? So the ideas are old, maybe the data wasn't there, but even if the data was there, the computation certainly wasn't there, right? So you've got this situation where machine learning needs lots of computation. At the same time, Moore's law is basically slowing down, right? So Moore's law, as most people know, talks about the doubling of transistors every 18 months to 2 years. But what people don't know is that Moore's law may be slowing down, but that's not the real problem. The real problem is this other related law or scaling factor called Dennard scaling.
Okay.
So Dennard scaling basically says, if I double the number of transistors on a chip, if I scale things the right way, I can keep the power the same. So I can double the number of transistors and keep the power the same. Now, if I take Dennard scaling away, I double the number of transistors and my power doubles too. That's now we're screwed, right? And that's the position we've been in, right? Which is why processors haven't been getting faster, because they're not, the ways that you speed up conventional processors are not power efficient. And we're already at the limit of our power dissipation, right? Especially, in almost anything you talk about, right? Whether it be your desktop, your laptop, or your mobile device. And so we're tapped out in terms of sort of what we can do with general purpose processors, given that we're power limited.
Yeah.
So the question then becomes, what do you do instead, right? And I think that is why it's such an interesting time in computer systems, because we've got this convergence of these two big trends, this need for insatiable amounts of computation to build machine learning models. At the same time, the conventional ideas for improving performance are basically stalled. And so this is kind of motivating all kinds of exploration into alternatives for general purpose processors. GPUs is an early entrant, but there are lots of companies investing, or lots of investment going in. So one of the questions after the talk was, how much investment do I think has gone into new hardware for AI? And I estimate billions.
I can see that.
Yeah.
Well, I mean, hardware companies typically take in much larger amounts than software. And I can think of a dozen easily.
Yeah, exactly. Right. So, Sambanova was well funded too. And so I just need to multiply that by, you quickly get to the billions.
Yeah.
So then working with Chris Ray has been all about playing these games, right?
Okay.
With efficiency and noise and so on to get higher, so when doing SGD, it's all about how many iterations does it take to get to a certain level of accuracy, right? And then what you really care about is not just how many iterations, but how long does each of those iterations take, right? So, the definition of the number of iterations is what we call statistical efficiency. And then the amount of time each iteration takes, we call hardware efficiency, right? So all kinds of games about, as you play with the noise, you affect statistical efficiency. But you're also potentially improving hardware efficiency. If you make hardware efficiency worse and statistical efficiency worse, then of course you're screwed up, right? But what typically you can do is make hardware efficiency much better without affecting statistical efficiency too much. So hog wild would be an example, right? You threw away the locks and iterations got faster, and now you didn't have to do too many extra, and you got to the same accurate result.
It strikes me that there's also economic efficiency in there that is not always perfectly correlated with either of those other two.
What efficiency would that be?
Meaning the cost of getting the result that you ultimately want.
Right. Yeah. And that may depend, right? Yeah.
So that kind of led you down to, into the hardware and kind of designing.
Yeah. So as I said, I've always been a hardware guy, but it's always been about. So I set up this problem that, hey, CPUs are kind of not going to improve anymore. GPUs are better, but they still fundamentally have issues. The question is, how can you design something that is both very efficient, especially in terms of power efficient, and also very flexible? Right? Because the most power efficient thing you could design would be exactly what you want, right? So you say, oh, here's my algorithm. I'm going to cast it directly into hardware and I'm going to go fab a chip based on that. And as long as that algorithm never changes, I'm golden. Now, that's the problem, right? There's a chart that I showed. So Moore's law says a number of transistors doubles every year, and if you look at the machine learning papers on arXiv, that's exceeding Moore's law. So we're doubling in the number of now. How many of those ideas are any good? Who knows, right? But there's probably some good ideas in that.
How many of those make their way to software, let alone hardware?
Yeah, exactly. Exactly. Good point. So what you really do need is a way to get both high efficiency and flexibility at the same time, because, hey, you need to be able to come up with new ideas and be able to implement them quickly, implement them both quickly in terms of performance and quickly in terms of how much time it took you to implement.
You mentioned that GPUs aren't perfect.
Yes.
And I happen to be overhearing a conversation here at NeurIPS yesterday or the day before, and it was kind of like, well, CPUs didn't work so well for this, but then we have GPUs and they solve all the problems, and it was kind of this always will suggestion. So maybe it's worth talking about what are some of the challenges that,
of GPUs.
of GPUs.
Well, GPUs, of course, were designed for graphics. And they still, of course, have some of the baggage associated with graphics. But GPUs...
Such as?
They've got extra hardware for doing graphics that you could care less about. So if you think about Silicon Areas as finite resource that you want to use, and you care about machine learning, if I use 20% of it to make graphics go fast, you say, hey, why are you taking my resources to do things I don't care about, right? So they still have those specific things, but more fundamentally, they are these. This architecture is designed to execute matrix multiply very efficiently. Okay, so
which sounds like a good thing. We need to do that.
We need to do that. So the question then becomes, is matrix multiply what you want ultimately? Ultimately, what you might want is some variant of matrix multiply that isn't quite what GPUs are good at. You might also want something that does sparse computation, right? Whereas they're doing dense matrix multiply very efficiently. Maybe you want something that does sparse. Maybe you want to be able to fuse lots of operators together to create this very weird function. And you would like to be able to do that without having to write some custom CUDA function. If I can delve into some of the intricacies, so when talking about efficiency, it has to do with how much of the silicon area actually goes into doing real work, right? So how much of the silicon area actually does multiply add? How much of the silicon area provides the memory resources for those multiply add units? And how much of the silicon area goes into what we call overhead, right? Managing threads, managing register contexts, doing things that are not really required to move the computation forward, but are necessary to support the programming model that came with GPUs, right? And then, what are some of the things that GPUs are lacking, right? So going back to this model of data analytics as being a set of data flow operators, right? So ideally, what you'd like to be able to do is cast that data flow graph directly into hardware. GPUs actually make that difficult because of the way that the memory is organized. So, but if you could do that efficiently, then there's all sorts of things that you could do that to make your computation be faster, and more importantly, to make it be much more efficient, right? Everybody talks about peak teraflops, but that's not the story, really. It really is about how optimally you can map any particular application to your hardware and what efficiency do you get. On a bunch of applications, the efficiency with which GPU gets are maybe, less than 10%, right? So it means less than 10% of the time you're actually kind of using the full capabilities of the GPU. So what that means is I could potentially build a machine that has a quarter of the capability, but if I could use it 90% of the time, I might be better off. I'm not saying I would build that kind of machine, but I'm trying, when you say what's the matter with GPUs, it's a fairly technical argument, but one that has real ramifications about what performance you get out of the end of the day. So you kind of combine these issues of sort of, overhead for doing things that are not machine learning, overhead for supporting a threading, graphics. Overhead for kind of supporting this programming model associated with CUDA. Not very efficient mapping of a bunch of these different networks. Okay. And then you see why there's room for other players to come in.
Okay. So I think I pulled you down a digression a little bit. But.
Yeah, that's fine. It's one I'm glad to talk about, but it's one that requires some level of understanding of what GPUs are, right?
Presumably, a big part of what you're working on are things that fix all of the above.
Yes, yeah, exactly. Yeah. How do you get,
Yeah. And so it sounds like then one of the maybe interesting bits here is what it means to build a computing architecture that's kind of more natively graph aware.
Yeah.
Can you talk a little bit about that?
Yeah. So I think some of the things that we found out was that it is about graphs, but it's about hierarchical graphs, right? So what you typically see when you kind of look below the covers of these graphs is that what you see is these operators, right? And the operators that you're probably familiar with from maybe the distributed execution world is map and reduce, right? So these are pretty basic operators, and depending on what functions you are operating over, they can be made fairly general. And so we take operators like MapReduce and a few others, and we nest them, and that gives you a lot more capability. And then once you have that graph, right, then you can think about how could you optimize that graph so that it uses memory very efficiently, so the communication is streamlined, so you can pipeline operations very efficiently. And then you think about how can I make that graph work very efficiently in hardware? What do I need to do? So that's what it's about. We at Stanford we worked on an architecture that we call plasticine. Plasticine. Yes. Okay. It's named after a children's modeling clay that is popular in Europe. I grew up in London, and so I played with it as a little boy. We're in Canada now. I'm sure they've got it in Canada. The closest thing to it in the States is called Play-Doh. Everybody played with Play-Doh. The key difference, and I think it's an important one from the naming point of view, is that if you leave Play-Doh out, it becomes a rock.
Right.
Hardens.
Crusty.
Well, turns out the plasticine's oil-based, so it never hardens.
And it's like that putty stuff.
Yeah, it's like a putty.
Eggs and stuff.
Yeah. Okay. It never hardens.
Got it.
So, but it's not silly. It does maintain your shape, right? So we're talking about gradations of
subtle nuances.
Subtle nuances. So, if you've ever seen the movie Wilson and Gromit, no, okay, or these claymation sorts of things.
Gumby.
Yeah, Gumby is probably plasticine. Yeah, because you could keep it in shape, take a picture, and then
dating myself.
Yeah, exactly. So plasticine.
And for the record, Gumby was before my time, but SNL.
Brought it back. Okay. It wasn't before mine. I can't. So plasticine's an architecture that was designed to execute these hierarchical data flow graphs very efficiently. Okay. So it's kind of native execution mode is these hierarchical data flow graphs. But there are a whole bunch of things that you want to do efficient machine learning execution. You want to do data flow graphs. You want to deal with sparsity, right?
Is there a quick way to rattle off what it means to do graphs in hardware? Are there kind of key principles?
So I think you can think of execution units as these nodes, right? And ways of communicating between them so that you can map these graphs directly onto these execution units, right? And then the way that you think about moving data through these is in terms of a pipeline of data that moves through it, right? So if you were only going to do things once, then you'd be wasting your time, right? But think of it as a multi-path intersecting assembly line, right? That's the way to think about how to kind of set things up. You really are kind of thinking about the cars being the data that kind of moves through this assembly line, and kind of at the end, the cars are complete, right? Okay. But maybe they're doing,
Is there some notion of having, if you've got some large graph and you're kind of mapping it to this more static substrate, then you're kind of swapping in parts of the graph?
Yeah. So that's a very good question, right? So, there's some machine learning. TensorFlow initially had no way. I mean, you got a static graph, right? You were done. And from a hardware point of view, you say, hooray, that's what I want. I can optimize the hell out of it. I map it to my substrate, and I'm not going to change it. But then you come along and say, sometimes I want to do this part of the graph. Sometimes I want to do that part of the graph. So you have to have some way of reprogramming things, right? And so a critical element of any architecture like this is how long does it take you to reprogram it, right? So that is a consideration, right?
Okay.
Because
we are talking about a reprogrammable thing as opposed to a general purpose.
Yeah. So think of it, as the assembly line metaphor is pretty good, right? On the factory floor, you set up the assembly line, and you're going to make the set of cars, and it's going to be this way for months, right? So you set it up and then you let it go, right? But if back when I used to be a graduate student at Michigan, people were talking about these flexible manufacturing lines, right? Because Michigan's, of course, Michigan, right? to say no more. So then maybe you're doing different things for every car, right? So now you have to have some way of adding some flexibility, having some reprogrammability.
Okay.
And so yes, now it's more flexible. But there's a truism in hardware design, and it goes back to something I said before about the fact that you could be more efficient if you only had to do one thing. Anytime you add flexibility, you are losing efficiency, right? And so there's always this game was, okay, how much extra flexibility am I going to add, and what's it going to do to my efficiency? And at some point you go too far. You say, screw it. And CPUs, of course, are at the extreme of that spectrum, right? They're very flexible on the flexibility side with huge amounts of overhead.
Right. And the other side would be, this is the model that I want to bake in the silicon.
Bake in silicon, and I can't change it. Yeah, very efficient, but then, So you get the spectrum, and you're saying, what's the ingenuity about what I do, about what things I can change and what things are fixed, right? And so that's the game. And then what's my compiler tool chain to target that, right? Right. Compiler tool chains for CPUs are very well established, right? There's C, LLVM, what have you. You can CUDA's pretty well established too. And some of these other architectures that you could imagine if you didn't have, they have many more degrees of freedom. So actually coming up with the right thing is more difficult. And B, they're just weird. In fact, weird in a good way. And then one of the things that they don't have is explicit instructions, right? So,
what does that mean?
Well, it means that, so an instruction would say...
Like explicit instructions that the, shift and move and all that low level stuff?
Right. Okay. So, they have them, but they're done spatially, right? So you say, okay, I'm going to, instead of this particular clock cycle, I'm going to do an add, and the next one I'm going to do a shift, and I'm executing an instruction. Then you say, no, you set it up. You're always going to do a shift. The end of time. It's more like configuration. That's what you're going to do. And I'm just
what I put in.
Yeah, I'm going to feed you data, and you're going to do what you do, right? And you're not going to change.
Okay.
And then the next step is going to do something else, right?
Got it.
And so
it's just how you get these things. So how do you make the data flow so that everything gets to the right place, so that the things that do their thing can do their thing?
You need a network.
Right.
So now you understand how you're building. You're building up kind of hardware which has some flexibility, but not too much, right? The key thing is where you put the flexibility and how you actually generate code for that.
Okay, interesting. And so,
but I should say it's all driven by the relatively static nature of at least the early machine learning, right? Right. It's become more flexible, but it's still relatively static compared to, say, pick your favorite other software space, right?
Right.
Yeah.
And so how does this tie into what you're doing at Sambanova?
So at Sambanova, we are doing a bunch of things. We are figuring out how to create a new platform for AI, right?
And what is platform can mean a lot of things.
Yeah. So
how low do you go? How high do you go?
Well, so high, low. Let me do low. Low's easy because we're going all the way to silicon.
Okay. Surprise.
Yeah, exactly. High, we're going to come up all the way to the frameworks.
Okay.
Yeah.
Okay.
And be very broad.
My understanding is still early. So.
It's still early, so I can't say much about what we're actually doing. But if I can talk about the founding team and sort of what capabilities they bring and that kind of.
But we don't need to go into the team. What I think is kind of interesting about this interview is that I'm not sure we ever transition from your background to to your talk. We kind of it all wove together, and so chronologically in time, and we've ended up at what you're doing now.
And so I have covered what I talked in my talk.
Did you?
Yeah, I did. We covered the whole space, and maybe I should recap, and then it'll be clear. So the recap is okay. I started out by saying, hey, we're in this era where machine learning is ascendant and Moore's law is descendant.
Right?
Yeah, it's gone. Right? We need to do things differently. We need new algorithms based around these ideas of trading off statistical efficiency for hardware efficiency. We need domain-specific languages for encoding them. We need optimizing compilers for generating code for a variety of different architectures, including new hardware accelerators, which are defined on top of these data flow operators. And then plasticine being an example.
So world, go build that.
Yeah.
Nice. Awesome. Well, Kunle, thank you so much for taking the time to chat with me and walk through
thank
all
you
that very cool stuff.
for reaching out, and it's been a pleasure.
Fantastic.
Yeah.
All right, everyone, that's our show for today. For more information on Kunle or any of the topics covered in this episode, visit twimlai.com/talk/211. You can also follow along with our NeurIPS series at twimlai.com/NeurIPS 2018. As always, thanks so much for listening, and catch you next time.